All right, let's take a look at our lesson today. We're going to be looking at the fundamental theorem of calculus. I know that sounds like a big deal, right? Fundamental theorem of calculus. This is our first look at it. There's really two parts to the fundamental theorem. Most textbooks would call this part two. I know, right? Part two. And part two has to do with something called the accumulation functions. So we're going to talk about the accumulation functions today. This would be like part two of the fundamental theorem. Okay? So what I have in this little dotted line box, this is really the background of what we're going to be doing today. And it all hinges around this relationship. Okay, the relationship between this function and this function. Really, really important. The relationship. If you can understand and remember the relationship between those two functions, you're going to be in a really good place. So what does that mean? If I do the integral or the antiderivative of f and I get g, then let's think about what that means about the relationship. We've talked about derivatives and antiderivatives. So if I do the antiderivative of f and get g, that means that f was the derivative of g. Okay, that's kind of subtle, but really, really important. So I'm just going to highlight it. This is a really big deal. This is a very important concept, because we're going to see it play out in so many different ways that this relationship holds, that this integrand, remember this is a vocab word, this part right here is called the integrand. More vocabulary words. This integrand right here, the antiderivative of this integrand gives me this function, gives me g. So I'm going to pause there for a second. Are there any questions about that? Does that make sense? Because we've done some antiderivatives. We're just delving into integration. All right, so with that in mind, just kind of keep that in the back of your mind. When I take the derivative of, now this is weird, right? This is weird looking right here. The derivative of the integral, it's like, what? So let's go back to some, let's just go back to like, let's talk about 3x squared plus 2. All right, let's say that's f, 3x squared plus 2. So if I take the derivative of that, right, I would take the derivative of that, that would just be 6x. Okay. If I integrate, so if I integrated this, it would put me back here with a plus c. Remember how we did that last time? So how they undo each other, they go back and forth. Okay, they undo each other. So if I am integrating f, and then I turn around and take the derivative of what I integrated, then I've undone what I have. Does that make sense? I undid it. So this would actually give me, the answer is f of x. And students are like, no, no way, that's not, I promise it works. And I'll show you, I'll give you an example of why it works. But if I take the derivative of the integral from a to x, this right here is just some kind of a number. Whatever kind of number, it doesn't really matter, just some kind of a number. To x, I will get f of x. Okay? Y'all are like, what? Okay. So here, notice on this one, these are reversed. That is a problem. Okay, that is a problem. They can't be reversed. Okay? All right, so this one, on this second one, this is the wrong order. The x, or the variable, needs to be in the upper bound, not the lower bound. All right, so what we have to do with this one is actually, there's a formula, which I won't go to right now. There's a formula on the other page. I'll just write it up here on our little formula chart that we were looking at. So if I do the integral from a to b of f of x dx, that's the same thing as the opposite of the integral of b to a of f of x dx. So that's a formula that we are allowed to use. We are allowed to change the order of the bounds by basically doing the opposite, multiplying the integral by a -1. And that's, I don't know if you can see that. Okay, that's a b. All right, so we're going to use this concept, this formula that's on your formula chart. We're going to use this concept on this second formula right here, because we really want those to be reversed. They have to be reversed. So what do you think the derivative of the integral from x to a of f of t would be? A negative f of x. That's what it would be. It would be negative f of x. Okay, are we okay? All right. So I'm going to finish the formulas, and then I'm going to demonstrate this first concept so that we're hopefully a little more comfortable with it. But let's finish through the formulas. So we've got the derivative of this integral is just f of x. The derivative of that integral, we'd have to flip the bounds, would be negative f of x. What if we had something other than an x up here? What if it was a function? Maybe it's like x squared, or maybe it's sine x, whatever it is. What if we have that? Because we will. Then what we would do, this is basically called the chain rule of this. We would take this, slide it in there, and then we would chain this. So my formula would be f of g of x. We would insert whatever is in this upper bound, whatever it is, whatever function is there. And then we would multiply by the derivative of the upper bound. It's the derivative of the upper bound. It's not multiplying by the derivative of the integrand. Students get that confused sometimes. Okay, just kind of keep that in mind. We would multiply by the derivative of what we inserted. What we inserted was that top function. All right, so this would be our result from that third formula. Okay, and the fourth one is the weirdest one of all. Of course, I leave the weirdest one for the last. This is a function and that's a function. Now that's kind of weird, right? What do we do if we have something like that? What if we do with that? So what we would do is we would start it the same as this third one. We're going to take this g of x and we're going to slide it in. That's what we're going to do. The same start as the third one. So let's go over here. So we would have f of g of x times the derivative of g of x, g prime of x. Now, how do we pull in the h? Well, we would subtract f of h of x times the derivative of h of x. So that's a little bit more intense, I guess, if you will. If you have a function on both the lower and the upper bound, we would have to do this scenario where we're actually subtracting. Okay, I want to pause here for a second. Are we okay with the formulas? So let me explain why, let me just do a little example out to the side, why this works just fine. Okay, let's look and see why it works just fine. So we're going to go over here, and I'm going to do the derivative of the integral. Let's do from, I don't know, 1 to x of 3x squared plus 2. Okay? So what we're going to do is I'm going to show you why this formula works so that hopefully you're comfortable with it and it's not upsetting. All right, so what I'm going to do is I'm going to do this part first. I'm going to do the integral, and then I'm going to do the derivative of my result. Okay, we're going to go through the whole thing. Okay, so we're going to do the antiderivative of this, y'all. We did antiderivatives last time. Hopefully the antiderivative is fairly comfortable. So we would add 1 to 2 and get 3, right? Then we would divide by 3, so that gives me x cubed plus. Then the antiderivative of 2 would be 2x. And we would put plus c, but this is going to be the first time we're going to look at a definite integral. A definite integral is one that has bounds. And this is actually part 1 of the fundamental theorem.
Would the antiderivative of 3x squared be, oh, never mind, sorry.
That's okay. Are we good?
Yeah.
Okay. So I still have this derivative business out here. Okay. So we've got this derivative. Okay, so the first fundamental theorem, which we will do in more detail later, we take the top one and we sub it in. And this is just an x. So it just is, what, x cubed plus 2x minus. And then we take the bottom one and we sub it in. Now you don't have to memorize this. We're gonna look at this again. I'm just showing you why this formula works so that hopefully we are comfortable with it. So I put a 1 in and I get 1 cubed, and I put 1 in there and I get 2. All right, so what am I doing? I'm doing the derivative of x cubed plus 2x. Let's see, minus 3. Help me with my arithmetic. That's right, isn't it? Arithmetic, yeah, 1 cubed plus, yeah. All right, so now let's do the derivative of that. The derivative of x cubed is what? 3x squared. The derivative of 2x is 2, and the derivative of 3 is 0. So I want you to see how we ended up with the exact same thing we started with. This is also the reason why we need a plus c. We talked about that last time. Why do you have to put a plus c if it's an indefinite integral? Because, well, what was that number? I mean, I don't know. Is it constant? So I'm going to pause there for a second. I'm just demonstrating, again, you don't have to memorize this fundamental theorem yet. I'm just demonstrating why this formula works. Okay? Why does this work? Because we're basically undoing the integration that we did. Okay? Questions about that? All right. So let's now investigate, what does it mean to be an accumulation function? What does that even mean? Okay, so let's go back to this one right here. What is an accumulation function? Okay. So this here, this is basically a picture of, this is an accumulation function. Okay, why? Because I've got a variable right here. See the x? I've got a variable. I'm going to be accumulating area as I move along. So this is a graph of f. So they tell us this is a graph of f, and we are supposed to find these values. Okay. So what we're doing is we're substituting this number in for x right here. That's what we're doing every time, because we're looking for big F of x. Right? Big F of x is going to be the integral from 0 to whichever of these numbers it's telling me. And I'm going to show you how the area adds up. It accumulates as we move. So for this first one, and they love for us to write out the integral, so please do that. We're going, the bottom bound, the lower bound is 0 because they set that. The upper bound, we're going to do the first one, is 0 of f of t dt. And as I look at the graph, remember we've practiced this before where we've calculated the area under the curve. The area from 0 to 0, is 0, right? There is no area from 0 to 0, so that would be 0. Okay. Let's do the next one. So now I'm going to do the integral from 0 to 1 of f of t dt. So what am I doing? I'm going from 0 to 1. I'm actually going to accumulate this area right here. I'm going to add all that up. So I would split this, and we had some practice with this. I would split this into two things. This would be like 2, right? And that's a triangle, half base times height. So that's 1. So this would be 2.5 or 2.5. So this would be 2.5. Okay. Now we want to do the integral. We're looking at the integral. We're doing 2 from 0 to 2 of f of t dt. So I still have to include this area right here that I already calculated, because we're going from 0 to 2, but we're going to add on, or we're going to accumulate area. We're going to add more on. So now I need to add on this part right here. This area needs to be included now. And this square, I would probably do this square, that's 1. And this one is another, 1/2. So I would do 2.5 plus 1.5. Oh, arithmetic. 2.5 plus 1.5. What is that, 4? So I would have 4. So we are accumulating area as we move. Okay. So now let's look at the next one. We're going to do the integral from 0 to 3 of f of t dt. Again, we're accumulating it. We've got to include all of the area we've added on before, plus, I'll just put it a different way. Also, we're going to include this one, and that's just, 1. That's the area of 1. So what is this? This would be 5. So the work that you would show, this down here, all of this stuff right here, this is the work that we're talking about. You would need to write the integrals out. Please don't just write a number as your answer. They love integrals. You need to write them down. Okay, so now we're going to 4, the integral from 0 to 4 of f of t dt. Okay, again, accumulating. So we still have the 5 area that we have already accumulated. So let's add in some more. So we've got this part right here. What would that be? That would be another 1/2, right? So we would be at 5.5. Now, the last one, so we're going to go the integral from 0 to 5 of f of t dt. This last one is underneath the x-axis. If the area, as we're integrating forward, if the area is under the x-axis, the sign of the area is negative. Okay, it's really not negative area. We don't really have something, that's not possible to have physically negative area. But the sign of the area, I know it's a nuance, and you're all like, so what, it's negative. Okay, I'm just saying, it's a nuance. The sign of the area is negative. Its sign is negative. And so as I am looking at this, this is a half, but we would actually count it as negative 1/2 because that area falls underneath the x-axis. Okay, so then I've accumulated all, I've got to 5.5, and then I have to take away a half, so then this would be 5. Okay, so I'm going to pause here for a second. Are we okay with the calculations that we did? And I want to explain to you what we actually have found. What do those numbers represent? So this is the derivative, right? This is the derivative. This is a picture of the derivative. What we just calculated with these integrals is position numbers. These are y values. These are y values of the position. This is a really important concept. These are y values of the position. In other words, if we wanted to see what the position looked like, we could graph those y values. it would give us a glimpse of what the position looks like. Okay? Okay, big concepts. We will continue to go over them time and time again. So if you're like, oh my gosh, what is she talking about? It's okay. We will continue to go over them. The second part, so are we good with accumulation? Yes, ma'am.
So when it's negative, you take it away from the one before, it doesn't just like cancel out.
Yeah, you basically, you're subtracting it from whatever you've accumulated so far. It just so happens that these two values right here happen to be the same, like they're both half. So it really does cancel that out. But what we want to think about is it's as we're adding area, we're going to add it if it's above the x-axis and we're going to subtract it if it's below. That's just a big picture. No matter what, wherever we're adding, we'll add the stuff above and subtract the stuff below. Okay? Anything else? Okay. So that is a picture of accumulation functions. We've just practiced one of them. What we're going to do now is we're going to work on problems that use these formulas up here that we just did. The derivative of the integral business, that stuff right there, okay? We're going to, the next page is all about those formulas, okay? And I hope that you're comfortable with the fact that the formulas work, okay? They work. I know they seem like, what? That's not even possible, but they work. Okay, so let's look at our examples. So what are they wanting us to do? They're wanting us to find big F prime. They want us to find big F prime. Okay, so let's think about what this is big F. So how would we even find big F prime? So what would we do? We would take the derivative of both sides. So it's like an equation, right? So we would do f prime of x equals d dx of 2 to the x of 3t squared plus 4t dt. So it's an equation, just like when you've been doing equations for years, right? You know, as long as you do that one, something to one side, if you do the same thing to the other, it's okay, it's balanced. So if I'm going to take the derivative of big F, I've got to take the derivative of the other side. Okay? So now we're using the formula from above, the derivative of the integral. It just evaporates, right? And this x just slides in everywhere there's a t. And so it is really that easy. It's just going to be 3x squared plus 4x. Are we okay? Good? Okay. Let's look at the next one. Okay, and notice I have this number on the bottom. That's, what we want. It doesn't matter what the number is. Any number works. Just some number on the bottom of x on the top. That's great. That's our first formula we looked at. Here, I do have a number on the bottom bound, lower bound. That's great. I do have something other than x. So this is x cubed. This means we're going to have to chain this. Okay, this would be the chain rule version of this fundamental theorem. Okay, so we still want f prime, so I take the derivative of both sides. So f prime of x equals d dx integral pi over 2 to x cubed of sine of t dt. That's what we're doing. Okay, what are we going to do? We're going to take this x cubed and we're going to slide it wherever there's a t. We're going to put it right here. Okay, so let's do that. So we slide that in. So f prime of x equals, big F prime, equals sine of x cubed. Now I have to chain it. Am I going to multiply it by the derivative of x cubed, or am I going to multiply it by the derivative of sine? What am I going to do? X cubed. I'm multiplying that. I'm saying that again because students get confused with that, right? We multiply by the derivative of the function that was on the bound, not the integrand. I'm multiplying by the derivative of x cubed, and the derivative of x cubed is what? 3x squared. So I'm fine if you leave it written like that. The normal way to write it would be to put this polynomial part, this 3x squared, in front. Again, as long as it's clearly separated, I'm okay. If you leave it written like the one above, I'm just going to rewrite it for fun, just for fun. And so that would be my answer. Okay, so that's the chain rule part. We good? Okay. Let's look at number 4. Okay, that's weird. I don't even have a regular looking function. It's just this weird h of t business. But we can deal with that, right? It's okay. It's fine. So f prime of x is going to be d dx of 1 to 4x of h of t dt. Okay, I'm just rewriting it, taking the derivative of both sides. So f prime of x is, so what do? We're going to do the same thing we've been doing. We're going to take this, we're going to slide it right there, right in place of the t. Okay, so that would be h of 4x. Am I done? No. I have to multiply by what? By the derivative of 4x, right? What's the derivative of 4x? 4. And again, I'll rewrite it just so, so it's perfectly clear. So it's 4h of 4x. And that's perfectly fine. We don't know what h is. If we did, we could do more with it, but we don't. So it's fine. Okay. We good? All right. Let's look at, okay, these last two are the really, really super weird ones because they're the ones where we've got to use this. Let me just go back here. This last formula right here where we've got like a function on the lower bound and a function on the upper bound. We're going to have to do this. Okay, this subtraction business. Okay, so let's go take a look at those two questions. All right, so what are we doing? We're going to do f prime of x is d dx of negative x to x of ft dt. Okay, so I'm doing the derivative of both sides. All right, here we go. We can do this. So f prime of x is going to be, so the formula tells us to take, we still start with the upper bound. We still start with this upper one, and we're going to slide it in there. Okay, so we've got 5x. Now, the derivative of x is 1. I can go ahead and put that there. That's fine, just to be in the habit. Minus, because that's what the formula tells me to do. I didn't do a minus because this is negative. I did minus because the formula tells me to. Now I'm going to take this one and slide it in. So it is what? 5 times negative x times, now the derivative, this is not a regular old x. I have to change that one. The derivative of negative x is what? Negative 1. Okay. Now it's a matter of cleaning this up. This is just a bit of a mess. So what do we have? We've got 5x, 3 minuses, goodness. Minus 5x. Oh, that's kind of disappointing. It all disappears. Okay. All right. That's the way we play it. That's fine. The derivative is 0. That's okay. 5x minus 5x is 0. Okay, one more. Okay, a little bit crazier, but that's all right. So we still have two bounds. So let's rewrite it. So we're going to do the derivative of both sides. F prime of x equals d dx 2x to 3x of t squared minus t dt. Okay. So we have a two-parter. So we're going to take this one, and we're going to slide it in everywhere there's a t. We have to place that. So f prime of x is. So I slide that in, so 3x goes in place of where this t is, minus 3x. Do I have to do anything with the 3x? I do. I have to chain it, right? So this whole thing is going to be multiplied by 3. Okay, minus, because that's what the formula does. Now we're going to work on this lower bound, and we're going to do the same thing. We're going to insert it everywhere there's a t. Okay, so we've got, what, 2x squared minus 2x. Do I need to do anything to the 2x? Yes? I have to chain it. So times 2. Now it's just a matter of algebra, distributing combining like terms. The most fun part of calculus is algebra, right? Y'all are like, no? You lost your mind? Okay, so here we go. Let's do our algebra. So what is this? We know this is not 3x squared, right? 3 squared x squared. We know that whole rule. I'm sure we do. 9x squared minus 3x. I'm going to need to multiply that by 3 in just a second. Then we've got, what, 4x squared minus 2x. Multiplying that by 2. Let's see. Oh, arithmetic. 3 times 9, what is that? 27 minus 9x minus 2 times 4, what is that? 8x squared minus 4x. When I'm subtracting more than one term, I do this every time. I hope that you do as well. So, because one of the most common errors is to forget to distribute the negative to the second term, right? I'm sure it's gotten all of us before at one time or another. So please be cautious. So I've got 27x squared minus 8x squared. Oh goodness, 27 minus 8, what is that? 19, right? 19, is it 18? 27? 27, oh sorry, 27 minus 8. Is that 19? Okay, good. And then negative 9x minus a minus, so plus 4x is what? Minus 5x. All right, how we doing?